Okay, so now we've reduced the problem to this. If big H of s is this function, then all we need to do is find little h of t, and then we'll be able to solve our original differential equation by using the property of multiplying by unit step functions. Okay, unfortunately this is a little bit trickier than expected. So first we need to do partial fractions because we notice from our table we don't have anything greater than degree 2 unless it's fully factored into a linear term to some power. So that's not this. So we're going to say 1 over s times 2s squared plus s plus 2. This is an irreducible quadratic. So this is a over s plus, and then the most general thing is bs plus c in the numerator, 2s squared plus s plus 2. Okay, that has to be equal. If we find a common denominator, we see that a times 2s squared plus s plus 2 plus s times this, we'll go ahead and distribute that because it's easy, plus cs has to equal 1. The numerators have to be the same. So let's see, what is the s squared coefficient? Here we have 2a plus b, and over here we have 0, so those have to be the same. The s coefficient, a plus c, and over here we have 0, so those have to be the same. And the constant coefficient, which is just 2a, and over here we have 1. Okay, so that means a is 1/2, and then substituting 1 in for 2a in equation 1, we'll say, we'll get 1 plus b equals 0, so b is -1, and then substituting a into equation 2, we get 1/2 plus c equals 0, so c is -1/2. Okay, cool. So now our function h of s is in a partial fraction decomposed form. 1/2 times 1 over s, that's putting the a in. We'll put a minus sign out here. We'll leave the s and the 1/2. Normally I would say get rid of fractions, but actually in a second we're going to create more. And I'll show you why. Okay, that's partial fraction decomposed version. We see this 2 in the bottom. There's nothing here in the whole table with a 2s squared in the bottom. And in fact, every time we have s squared, either it's a sum of squares, a difference of squares, or it's a sum of like completed squares, or it's a higher power linear term. Okay, so let's keep that in mind. We need to get rid of this 2, so we'll just take out a factor of 1/2 from here. Okay, this is 1/2 times 1 over s minus, take out a 1/2, so we're taking out a 2 from the bottom. We'll leave an s plus 1/2 in the top. We'll have an s squared plus s over 2 plus 1 in the bottom. And now, so we can't get rid of this linear s term. These ones don't have both linear and quadratic, so that must mean it comes from one of these. And we have to complete the square to get it looking like one of these. And actually we have an s in the top, so it's certainly this one. Okay, so let's complete the square here. First one's fine. 1 over s we know the inverse Laplace transform of. Down here, let's see, half of 1/2 is 1/4. 1/4 squared is 16. So I actually, if I write plus 1 over 16, this is s plus 1/4 quantity squared. And then to make up 1, I need to add another 15 over 16. Now make sure you agree this denominator is the same as this denominator. Okay, in the top, so this is s plus 1/4 squared. So here we're looking at one of these. A is -1/4. So that means we need an s plus 1/4 in the top as well. I have an s plus 1/2. So this is s plus 1/4 plus another 1/4. Okay, it's getting quite ugly. You got to keep going. Okay, this is 1 over 2 times 1 over s minus 1/2. And then I'll write this part separately. So this is exactly how I want it now. S plus 1/4. And then this is s plus 1/4 squared plus 15 over 16. And notice that these guys have a b squared here. So I'm going to write this is the root of 15 over 4 quantity squared. That's what that is. Plus, now I have a 1/4 in the top. What did we want? Well, now we're looking at the thing without the s, so we're here. But we need it to be the same as b. I don't have that. I have 1/4. I want root 15 over 4. Okay, in math, if I want something, I take it. So I'm just going to write root 15 over 4. Fix it later. There should still be a 1/2 out here. And then the bottom is s plus 1/4 squared plus root 15 over 4 squared. This is what I want. It's not what I had. I had 1/4. So I multiplied by the top by root 15. I need to multiply the bottom by root 15. So I'll just consume it into that constant, and it'll be fine. Okay, this is now in good form, apparently, to take inverse Laplace transforms of. So I can write little h of t is, what is that? This is inverse Laplace transform of 1 over s is 1. So this is just 1/2 minus 1/2 times inverse Laplace transform of this. I worked very hard to get it to look like this one. S plus 1/4 in the top. So a is negative 1/4, and b is root 15 over 4. So I'm going to write e to the minus 1/4 t, e to the minus t over 4, cosine root 15 over 4 t. And then I'm going to add 1 over 2 root 15. And then this other thing, now we worked somewhat hard to get it to look like this. So it's the same thing but sine. So this is, we still need an e to the negative t over 4 sine of root 15 over 4 t. And hopefully at this point you believe that we could have used method of undetermined coefficients, because these are looking a lot like things that would have come out of that. Okay, we found little h of t. We're almost done. All we need to do now is we need to incorporate that back into here. So let's look one more time at the Laplace transform table. So we're looking at line 12. No, line 13. This was the property we talked about before. We have the Laplace transform multiplied by e to some power. So the inverse is going to be whatever the inverse Laplace transform was for this function, shifted by c to the right, times the unit step function at c. So here we're taking unit step function at 5 times little h shifted by 5 minus, this is if we expand this out, unit step function at 20 and then little h shifted by 20, where little h is this ugly thing. So you actually get 1, 2, 3 terms here, so you'll get 6 terms here, each one multiplied by a unit step function. Lots of fun.